There are somewhere between 2 and 4 million fungal species on this planet. We have described about 150,000 of them. Only a few hundred can infect a human body, and the reason is not your immune system. It is not your skin or your chemistry. It is a single number, 37 degrees Celsius, your core temperature. Most fungi cannot survive it. They top out well below it. And that thermal wall is the only reason a group that has devastated insects, plants, amphibians, and bats has mostly left you alone. But the planet is warming, and a warming world is a laboratory. And in that laboratory, something is being selected for. Not intelligence, not intention, just a little more heat tolerance. Which is the same thing as saying, it is being selected for you. Mammalian endothermy, the ability to generate and hold internal heat, is one of the great evolutionary innovations. We maintain a constant core temperature regardless of the environment around us. And for decades, mycologists have argued that this trait functions as something unexpected, an antifungal firewall. The argument is straightforward. The vast majority of fungi grow best between 20 and 30 degrees Celsius. Push them past 35 and their enzymes misfold. Their membranes destabilize. Their growth slows and then stops. 37 degrees is not comfortable for them. It is lethal. A bat, a whale, a human. We walk through the world as thermal no-fly zones. Fungi can colonize our skin surface, our cool extremities, our lungs where air cools. But deep tissue, blood, organs, that interior is off limits because it is too hot. This is why fungal infections in mammals are relatively rare. Not because fungi are weak, because we are warm. Consider the scale. 2 to 4 million fungal species. That is an estimate, and it is probably conservative. Of those, roughly 150,000 have been formally described by science. The rest exist unnamed, uncatalogued, living in soil and water and leaf litter and the guts of insects. Most will never matter to you. Most are decomposers, partners, quiet recyclers. But the gap between described and undescribed is not just academic. It means there is an enormous reservoir of organisms whose thermal limits we have never measured. We do not know which ones sit just below the human boundary. We do not know how close they already are. What we do know is this: the boundary is narrow. A thermal tolerance chart for common environmental fungi shows growth peaks clustered between 25 and 30 degrees, then a sharp cliff. 37 sits just past the edge. 1 or 2 degrees of adaptation could close that gap entirely. 1 degree is all that separates a harmless soil organism from something that can live inside you. So what happens when a host population has no thermal defense? When the firewall is absent, or when a fungus finds a way around it? We do not need to imagine. We can watch it, because it has already happened. Not in mammals, not yet, but in organisms whose immune systems and whose body temperatures offered no barrier at all. The results are written in extinction. They are written in silence where there used to be sound, and they are written in a pattern that is the same every time. A pathogen encounters a naive host population. The host has never seen this organism before. It has no evolved resistance. The fungus spreads through skin, through water, through shared hibernation spaces. It does not need to be aggressive. It just needs to grow. And it grows because nothing stops it. What follows is not a disease outbreak in the way we usually think of one. It is a demographic collapse. A removal of species from landscapes where they existed for tens of millions of years. And it has happened more than once. The first organism is Batrachochytrium dendrobatidis. Researchers call it BD. It is a chytrid fungus, an ancient lineage that normally feeds on keratin in soil and on dead matter. But BD found a new substrate, Amphibian skin. Frogs and salamanders breathe and drink through their skin. It is a living membrane, thin, moist, constantly exposed. BD colonizes that membrane and thickens it. The keratin hardens. The skin stops passing electrolytes. The animal's heart stops. Since BD was identified, it has been implicated in the decline of roughly 500 amphibian species. About 90 are presumed extinct. It is the worst disease-driven loss of biodiversity ever recorded. Not by habitat destruction, not by climate alone, by a fungus. BD moved through populations that had no co-evolutionary history with it. No resistance. No thermal buffer. Their bodies were the right temperature and the right substrate, and that was enough. Entire species vanished from streams and ponds where they had persisted since before the last ice age. The mechanism was not dramatic. There was no visible catastrophe. The ponds just went quiet. Look at what BD actually does to a single animal. Spores land on wet skin. They germinate. Tube-like hyphae penetrate the outer keratin layer and begin to grow downward into the epidermis. The fungus does not produce a toxin in the classical sense. It does not need to. It simply disrupts the skin's normal function. Amphibian skin regulates sodium and potassium. When that regulation fails, electrolyte imbalance follows. Potassium drops. The heart's electrical signaling depends on potassium. When it falls far enough, the heartbeat becomes irregular. Then it stops. The animal dies in a matter of weeks, sometimes days, often sitting in shallow water where it tried to cool itself. This is what a fungus does to a host with no defense. It does not orchestrate a sophisticated attack. It grows. And the growth itself is lethal because the host's biology is built around a tissue that the fungus happens to consume. That is the pattern. A naive host, a compatible substrate, the right temperature. The result is always the same: removal. The second case is different in mechanism but identical in pattern. A fungus, a naive host, a population with no resistance. Collapse. In the winter of 2006, a biologist in a cave near Albany, New York, noticed bats with white muzzles. The white was a fungus growing on their faces. The organism was identified as Pseudogymnoascus destructans. It came from Europe, where bats had co-evolved with it and survived. North American bats had not. The fungus thrives in cold cave environments, exactly the conditions where bats hibernate. It grows on the bare skin of the muzzle, ears, and wings. It does not kill directly. It kills by waking them up. Hibernating bats drop their body temperature to near freezing to conserve energy. They survive on stored fat through the winter. Every time they warm fully, even for an hour, they burn fat that took weeks to accumulate. The fungus causes irritation that triggers these arousals again and again and again. Picture a hibernating bat. Its metabolism is nearly shut down. Its body temperature matches the cave, maybe 4 degrees Celsius. Its immune system is suppressed. It is, in effect, a dormant host with its defenses offline. Pseudogymnoascus destructans grows across the wing membrane. The wings are vascular. They are thin. They are the perfect substrate. The growth causes discomfort. The bat stirs. It warms. It burns fat. Then it cools again. It stirs again. It burns more fat. By midwinter, the fat reserves are gone. The bat either starves or flies out into the cold to search for insects that are not there. Since 2006, white nose syndrome has killed millions of North American bats. In some hibernating species, declines have exceeded 90%. Entire colonies gone. Caves that held thousands of animals now hold none. And the pathogen persists in the cave substrate. It remains viable. It waits for the next bat that enters. It is a pathogen that kills during sleep. That is the detail that matters. It does not need the host active. It needs the host still. Now bring this to us. In 2009, a new fungus was described from the ear canal of a patient in Japan, Candida auris. It was unlike most Candida species that live harmlessly on human skin and mucosa. This one was different. It survives at 37 degrees. It grows at 37 degrees. It tolerates 42 degrees. That thermal tolerance is the detail that should hold your attention. Candida auris does not stop at the mammalian firewall. It walks through it. It colonizes skin, catheters, IV lines, and hospital surfaces. It persists on stainless steel, plastic, and fabric for weeks. Standard disinfection protocols do not always remove it. It is resistant to fluconazole, often resistant to amphotericin B, sometimes resistant to everything in the antifungal arsenal. The CDC designated it an urgent threat. In invasive cases, where it reaches the bloodstream, mortality runs between 30 and 60%. The hospital is its ecosystem. Sick patients are its substrate. Negative pressure rooms, sterile corridors, gloved hands, swabbed bed rails. These are not barriers, they are surfaces. Candida auris forms biofilms, thin layers of cells and secreted polymers that adhere to surfaces and shield the organism beneath. On a bed rail, on a ventilator tube, on a blood pressure cuff, those biofilms survive cleaning. They survive drying. They survive UV light in some cases. A patient touches the surface. The fungus transfers to skin. It may do nothing. It may colonize harmlessly for weeks. Then the patient's immune system is compromised by treatment, by illness, by age. The fungus enters through a catheter site or a wound. It reaches the bloodstream. It disseminates to organs. And the drugs that should stop it do not, because the organism has already encountered them and adapted. Candida auris has now been detected on 6 continents. Each first detection plotted on a timeline shows a spreading pattern. It is not a single outbreak. It is the emergence of a thermally adapted fungus in the one environment where naive, vulnerable hosts are concentrated: the hospital. Here is the mechanism that should unsettle you. Fungi do not need to decide to become heat tolerant. They do not need to plan. Evolution selects. In a warming world, organisms that can grow at higher temperatures survive. Those that cannot, die. Every generation, the selection pressure pushes the thermal boundary upward by fractions of a degree. It is a ratchet. It only moves one direction. A warmer climate means warmer soil, warmer water, warmer surfaces. Fungi adapted to those warmer environments sit closer to the human boundary. Some are already there. Candida auris is already there. The thermal adaptation argument is not speculative. It is observation. The planet has warmed roughly 1 degree Celsius since pre-industrial times. That is the same order of magnitude as the gap between the maximum growth temperature of most environmental fungi and human core temperature. The firewall is not being broken. It is being eroded. Degree by degree, generation by generation. This is not a prophecy. No one can say which species will cross next, or when, or whether it will matter. Selection pressure is not the same as prediction. Most fungi will never adapt. Most that adapt will never reach a human host. Most that reach a host will never cause disease. The honest caveat is that emergence depends on many factors converging, but the caveat does not change the direction. The thermal ratchet moves forward. The planet warms. The gap narrows. And somewhere in soil that has never been sampled, on a surface that has never been swabbed, in a cave or a pond or a hospital corridor that has never been watched. An organism is growing at a temperature it could not have grown at a century ago. It does not know you exist. It does not need to.